Well, it's a great pleasure and honor actually to give this seminar, this Monday seminar. I wish I could have attended more of them, but all the ones I've attended were really great. I hope I will be up to the standards. Okay, so today I will show you some work that we've been doing over the over the last 10 years, try to sum up things. So over the last 10 years on deep seismicity. So this is mainly, of course, the work of others. And in particular, I would like to salute a few PhD students, Arefe, Marie Baissé, Sarah Insel, Thomas Ferrand, a few master students, Clémence Degre and Sandra Babinski, who've been really instrumental in all the work I will show you about today. So as the title said, we're going to go deeper and deeper in the subduction zones. And obviously this is too much to cover in a single seminar, so I will just mainly emphasize on tectonic tremors that we think we've probably been able to reproduce not so long ago in the lab, and also some work that has been done in the last year or so, in the last years or so, on deep focus earthquake triggering. And all this can be summed up by the paramount role of mineral phase transitions in source seismology. This is one of my opinion. I'm ready to defend it. So, okay, so the first thing is tectonic tremor and LFEs. So tectonic tremors were discovered about 20 years ago now, famously in Japan. Here you see a location map of tremors in a narrow zone along the subduction channel. Here you have the Shikoku Island, and here the main island of Honshu. And you see that those tremors locate in a narrow zone in the subduction zone, and here, which corresponds actually also to a narrow pressure and temperature conditions along the subduction zones. If you look at seismic tomography work that has been done in the same area, here what you see in gray, you see the location of tremors, and you see that often below the tremors, but not always, you have low P wave anomalies, but in particular below tremors, you have this zone that has been shown for also almost 20 years now, of a high VPVS ratio, so high fluid content in this area. And so again, those observation of the high VPVS anomalies that were just below are generally interpreted as high pore fluid pressure zone, and generally the metamorphic reactions, especially dehydration, are invoked both as a source of fluid and fluid migration. So we believe that the fluid is produced and is going up. However, both these features, how dehydration are linked to tremor generation and high VPVS ratio, remains poorly understood, and at least there is limited experimental evidence performed at in situ PT condition for the moment. So if we go deeper in the subduction zone now, it's been 100 years approximately that we know of that earthquake happen below the surface of the Earth, and they can happen as you see here in this figure from an old figure from Froelich in 1987, where you see the number of earthquakes per year as a function of depth, and you see that there is from about 50-kilometer depth, there is an exponential decay of seismicity down to a minimum reached around 300 or 350 kilometers. And then there is a second maximum that happened actually in the subduction zone. And so these earthquakes happen at PT conditions that are of several gigapascals, and probably in temperature conditions that are somewhere between 500 and 1000 degrees C. So they remained a challenge, a conceptual challenge for seismology and for mechanics for a number of years, and they still remain so. They actually, all this deep, or at least 99% of this deep seismicity actually happen along subduction zone, where you see here in blue the intermediate depth earthquake. So the intermediate depth earthquake would be the earthquake between 50 and 350 kilometer depths. And you see they happen almost everywhere in all subduction zone, even in the small Caribbean subduction zone, even in Mexico, etc. And below is the red seismicity, the transition zone seismicity or deep focus earthquake, which actually doesn't happen everywhere, happen only in a given number of subduction zones, namely the coldest ones. Hot subduction zones seem not to be able to produce like earthquake in the transition zone. So as early as 1945, it was suggested by Percy Bridgman that possibly these deep earthquakes would be linked to phase transition. And in a paper he wrote, there is a theoretical possibility, which should be kept in mind, that there is no thermodynamic reason why transition should not occur under shearing stress, although at that time no example of the phenomena had been positively identified. Okay, so for the intermediate depth seismicity, we can look at what transition can be at play. And there is this nice paper by Yuval Bonnet a few years ago now in JRL, which I think is kind of compelling to show how dehydration or water at least should play a role in this intermediate depth seismicity. Here you see a plot of intermediate rate seismicity as a function of maximum fault throw, and maximum fault throw is the amount basically of normal fault that you produce during the outer rise bending of the plate, as the plate is actually being bent to be able to subduct. And the more you bend it, the more you fracture it, and the more you fracture it, the more you have water that can enter deep into the mantle. And basically, the more water deep into the mantle, the more intermediate depth seismicity. And so here you see the case of 17 subduction zones around the world. You can actually see that in a given subduction zone only. So this is a beautiful paper, a seismic reflection and refraction paper along the Aleutian subduction zone, where two seismic surveys were performed here along the Schubnel gap and along the Semidi segment. If you look at the production of intermediate depth seismicity here in yellow and red, what you see is that there is a lot of intermediate depth seismicity just north of this Schubnel gap, and there is almost no intermediate depth seismicity above this, below this Semidi segment. And when you look at the seismic profile, what you see is that along the Schubnel gap, which produces earthquake, there is a lot of fault, all these little arrows. This is all the bending faults. And when you do tomography, what you see is that the mantle has reduced upper mantle velocities. And so there is probably a large amount of hydration material here. So faulting, water, production probably of serpentine, or at least a hydrated mineral. And in the end, that actually leads to intermediate depth seismicity, whether here, almost no fault, little variation in the upper mantle velocities, and no or very little intermediate depths earthquake. Okay, so when we move now to the deep focus earthquake, one of the things that I said earlier is that not all subduction zones produce deep focus earthquake. In fact, only the coldest subduction zones produce earthquake, and this is a famous plot by a paper by Steve Kirby in 1995, where if you look at the deepest earthquake in a given subduction zone as a function of the thermal parameter being a proxy for how cold and how fast the slab is going. So the thermal parameter exactly is the age of the plate at the trench multiplied by the vertical velocity, the descent rate. Basically, you see that for thermal parameters below 5,000, there is no transition zone earthquake, and above 5,000, you start to have earthquake in the transition zone. And that is explained by the fact that from using the kinetics of the days, kinetics mainly constrained by Dave Ruby, you could actually say that if you have a young, slow, hot slab, and this is one of the first thermomechanical models ever done, if you can the cold anomaly, basically because the slab is young and is slow, and is hot. The cold anomaly doesn't penetrate much deeper than 300 kilometer depth. This isotherm here is the 600 isotherm. Whether if you have a very old and fast descending slab or very cold, basically you can actually have a very cold anomaly that penetrates far into the transition zone here between 400 and 600 kilometer, and you see that you have a piece of the slab here that remains below the 600 isotherm, and so basically the olivine here, which should transform into its high pressure form at the 410 boundary, basically is prevented from doing so for kinetic reasons. Another striking thing about the deep focus earthquake is the dependence of the B value of the deep earthquake population on the thermal parameter. And here you see that the B value, this is a compilation from a paper by Zhongwen Zhan in 2017, where in green you see the B value measured along several subduction zones. For the intermediate depth seismicity, it's around 1. Whether this is the B value measured for deep earthquake, for deep focus earthquake, so transition zone earthquake as a function of thermal parameter. And there is this weird observation that actually hot slabs have a low B value, so tend to produce more large earthquake and less small earthquake, whether like the coldest slab on Earth, Tonga, actually produces a very large amount of small earthquake, but no real big earthquake, although there was 2 magnitude 8s in 2018 or something like this. I don't remember. Yeah, 2018, I think. Okay, so the model can be summarized for the intermediate depths and deep focus earthquake as the green model. I like to call it the green model in honor of Harry Green, where basically the intermediate depth earthquake are linked to dehydration, and particularly the ones that the earthquake that happened in the lower Wadati-Benioff plain would be linked to serpentine dehydration, whether the earthquake in the transition zone here occur because of the olivine spinel phase transitions. And tremors, it's still an open question. Okay, so this is a bit of a background. So what I will show you today is how we can try to tackle this problem with rock mechanics, basically rock mechanics experiment. And so I will first show you a new machine that has been installed at ENS a few years ago now, which is some sort of a modern Griggs apparatus, which enables us to do acoustic monitoring. And then I will show you how, using this, we can actually show, measure VP, have a proxy for VPVS, and record tremor-like signal during dehydration under hydrostatic conditions. And then I will go on some work that we've just done on the olivine spinel transition and the triggering of deep focus earthquake. So, okay, so first the machine. So, as I said, it's a modern Griggs. This is the original drawing of the Griggs apparatus, which is an apparatus from the 60s. This is our version of it, so it's very similar. The sample is located here. It's a solid medium pressure apparatus where the confining, where we'll come back to that, is actually, and the pressure is given through a solid medium, which is salt. And it enables us to go to 5 GPa and up to 1000 degrees. And the only modernity in all this is actually the add-on of those 2 transducers here. You have a top transducer and a bottom transducer that can enable us to record and listen to the sample. Okay, so this is the sample assembly. So we push on this piece here, which actually in the end exerts confining pressure, and then we can push in the center here, and that actually will give us the differential stress, and so we can deform rocks at really high pressure and temperature conditions. While doing this, we can actually send waves through the rocks. So here you have a source and we send a signal. So this signal is a very high frequency signal because our sample is only 10 millimeter. So it's typically a 10 megahertz signal. So we have with a wavelength of around 0.1 millimeter. So we have 10 wavelengths in our sample, basically. Obviously, there is a lot of noise, so there is a lot of stacking we need to do. We need to go to sampling frequency that is above 10 megahertz, etc., etc. And in the end, we have a very clear arrival. Here you see one typical signal. The positive is red, the negative is blue. This is the travel time along the entire column. And here you see the evolution of travel time during the experiment as the sample is being shortened. And we produce those images that actually look a little bit like receiver functions. And I think there is a lot of development to do applying like modern seismology techniques to treat these images. But this is another seminar. So we need obviously to make a very careful calibration because the travel time between the two here is about 20 microseconds and only 1 microsecond is in the sample. So there was a large amount of calibration that was done by RFA Moret-Vand, and there is more in her paper in technical physics in 2021. Okay, so the bottom transducer we can also use as a passive acoustic emission transducer just to record to the rock. And so in that case, we use a PNS wave transducer, so which actually enables us for a given acoustic emission to pick the P and the S arrival, and the difference time between TP and TS gives us a proxy for a 1D location along the column. And so here is the acoustic emission that are expected to be in the sample when they have a TP minus TS of around 3 to 4 microseconds approximately. Okay, so this is the two things we can do. And so the first thing I will show you is how we can apply it to serpentine dehydration under hydrostatic condition. So during her PhD, RFA took samples of an antigorite that we had been working on since the work of Julien Gaskin. So it's been more than 10 years, actually, but we're working on the same block of antigorite. The nice thing is like Greek samples are very small, so we can make a hell of a lot of them in a very small block. Okay, and what she did is she took this antigorite under this PT condition here. This is pressure, this is temperature, and this is the rather complicated phase diagram of antigorite here, where at low pressure, antigorite first breaks down around 500 degrees, and then there is several transformations. And the final one being here, antigorite gives water plus forsterite, olivine plus enstatite, orthopyroxene. And you see that most of the points that we tested were actually in this field where the dehydration should be complete. So what we did, so we have antigorite that produce olivine plus pyroxene plus water. At the beginning, we're at 300 degrees. We just ramp up the temperature 10 degrees a minute to the target temperature, where we stay around 1 hour, an hour or two. So the entire experiment is actually quite fast. It takes maybe less than an hour and a half. So if we measure the wave speed and we see here the evolution of P wave velocity as a function of temperature for those 3 points here, what you see is that if we go just at the limit of the transformation, the P wave velocity starts to decrease. And then if we go a little higher at 650 degrees, we have a decrease, more decrease. And this is a subsequent decrease because you see we started at 6.5 and we end up at 5.5. And then if we do the complete reaction, we go from 6.5 to about 4.5 kilometers per second. So this is a very substantial decrease in P wave velocity. And here you see the same plots as a function of time with this typical sigmoidal shape that I will come back to just a little after that. So we can now look at the effect of pressure. So it's the same. Now we look at from 1 to 2.5 GPa. And
hey, Alex, sorry to interrupt, Chris. Can you go back to the slide before? I'm confused by the plot A at the top right, because the x-axis is temperature, right?
Yes.
What does it mean to have a line that says 600? Starts at 600?
sorry.
The top right plot.
Top right plot, yeah, it's
Yeah.
here. Yeah.
So you have
So
curious, yeah, why don't I mean,
yeah, so this is the target temperature, sorry.
I see.
So this is the target temperature. So we stopped at 600 degrees, we stopped at 650. So you see here, this is, we increase the temperature until we reach the plateau. So this is the target temperature.
I see, okay, thanks.
Sorry. So as we increase the target temperature, the wave velocity drop becomes bigger and bigger.
Got it.
Okay.
Thank you.
So now this is the same now, but as a function of pressure. And what you see is that at 1 GPa, we have a substantial drop in P wave velocity. And this is at 1.5 GPa, 2.2 GPa, and at 2.5 GPa, the pressure, the wave velocity drop is much smaller. And again, we have those curves. They actually look sigmoidal, and they are very reminiscent of an Avramis curve. So what you're looking at here is basically the kinetics of the reaction itself. Exactly. So the Avramis equation for kinetics. Okay, so the thing is, so dehydration is linked to a drop in P wave velocity. That's an information, even at high pressure, I want to say. Okay, so that's an information in itself. And we have the VP seems to be related to a certain extent to the amount of reaction. So we can try to see if that's true when looking at the sample. So this is the sample as we increase the temperature at 1 GPa, where you see that the reaction initially, the black material is the reacted material and the white material is the initial antigoid. And you see that at the beginning, the reaction happens when you're close to the equilibrium along fractures. So you have a lot of fracture and you transition slowly to some sort of a reaction front, basically where here everything is reacted and here this is the front of reaction. And this is the same now when you, it's the contrary, when you go from pressure, when you increase the pressure, here you have, this is the same image as this one, you have a reaction front, and as you increase the pressure, you seem to have more and more fracturing going on. Okay, so one of the things is to try to understand why the wave velocity drop. And so you can write the reaction in a simplistic way where you say antigoid gives first steroid plus enstatite plus water in a stoichiometric way. And then you take the elastic moduli and the density of solids at the PT condition that we're working at using like a database, a thermodynamic database. For the minerals and for the fluid, we use the solution of the International Association for the properties of steam and water. Believe it or not, there is one, which actually gives you the thermodynamic properties of water for supercritical water. And then we use an effective elastic moduli using effective elastic medium, which is that of Jérôme Fortin, where basically you have a solid matrix in which you put fluid inclusion that are isolated completely. And what you see is that if you were to have no fluids, basically, obviously, the P wave velocity would increase as a function of reaction extent because you're replacing antigoid, which has a low P wave velocity, with forsterite and enstatite, which actually are stiffer material. And so the P wave velocity would increase. But if you were putting the water in spherical pores, basically there would be no shift in velocities. And the only way you can explain a drop in velocities as a function of reaction is by putting them in crack-like inclusion. So basically, it actually shows that indeed, like not only the reaction produces water, but it produces water that is actually incorporated even at high pressure into crack-like inclusion with small or to very small aspect ratio. And this has an important consequence because, in fact, once you've said that, you can actually predict, although we don't measure it, but we can predict the VPVS ratio as a function of reaction extent for a given crack-like inclusion of different aspect ratio. And indeed, as the inclusion gets narrower and narrower, or as its aspect ratio gets smaller and smaller, basically you will produce a higher and higher VPVS ratio. So again, we have this, there is good evidence to say, well, if you dehydrate material at high pressure, even if it's 1, 2 GPa, basically you will have a drop in velocity and an increase in the VPVS ratio as is seen in subduction zones environment. So again, so this is a good explanation of the tomographic observation done by our tomographic colleagues.
Alex, I have a quick question about that.
Yes.
Does this model capture the sigmoid that you were seeing in the experimental data too?
No, so it's a good question. So no, in fact, no. So yeah, it is capturing it to a certain extent because we are actually doing the reaction as a function of reaction extent. So you see here, you're plotting P wave velocity as a function of reaction extent. And so now if you give an Avrami's law for the reaction extent, basically your P wave velocity will actually give you the sigmoidal shape. So this is just a link between the reaction itself and the elasticity of the medium. And then you need to put the kinetics inside. But this is actually maybe more powerful because in fact, that actually tells us that we could investigate reaction kinetics outside of the synchrotron as generally done, just by using acoustics in this system. And this is another experimental perspective. Okay, so so another thing we can do during this experiment is record acoustic emission. So again, these are experiments that are performed under hydrostatic condition. This is 2.5 GPa, and what you see is a ramp from 100 degree to 800 degree, then back to 100 degree. So this is not a very nice plot, I'm sorry, but here you see the temperature ramping as a function of time during the day. So we started at 11, and we stopped at 3:30. And basically, you see that while we're ramping up the temperature, we produce a lot of acoustic emission in red here. And those are mainly what I will call acoustic emission of type 1. So where you clearly see a P and S wave, and they are very impulsive. And then during this phase from 400 to 800 degrees, what we record is those weird signal here that I will call acoustic emission of type 2. And that are not very impulsive, where it is impossible to distinguish the P and the S wave, etc. And then the most acoustic emission, and that people who do acoustic emission will always tell you, is upon unloading or cooling. And here you see like the acoustic emission produced upon cooling, again, which are acoustic emission of type 1 with clearly impulsive and with P and S wave arrival. Okay, so this is three signal. This is three typical signal, like obviously the nicest that we have recorded in our system. And I will just show them to you in front of tremor-like signals. And you see that they are very reminiscent of tremors, except here the time is 100 microseconds. So the question is really, is it possible to scale this result? Is it possible that tremors, which last like hundreds of seconds in the field, would only last a few hundreds of microseconds in our experiment? I want to say that we also measured the envelope of those acoustic emission, tremor-like acoustic emission, and they do follow some sort of a they do follow the Gutenberg-Richter law with a weird cutoff here that we don't understand, around magnitude minus 8.8 here, where we produce a lot of very, very tiny ones. And this is this is the cumulative frequency magnitude distribution that you see. And so we can try to do a simple scaling relationship. So in the lab, where our acoustic emission here have a typical, this is 2 spectrograms of acoustic emission. They have a typical frequency that is between 1 and 2 megahertz. And if you assume that the wavelength we're working out is typically between 50 microns and 1 millimeter, and if you apply now that those are linked to stress drop of around 1 to 100 kPa, that would give you the in the field, at least that's what has been described in the field, that would give you a length in the field of around 100 to 500 meters, and a frequency for the field that is between 1 and 4 hertz where they are observed. And then basically you have the right scaling between the lab laboratory observation here of the frequency divided by the laboratory by the tremor versus its length, and it's scaling of around 1 million. Okay, and so what we believe is that what we're hearing is basically the water flowing in pipes that actually is making the vibration. One of the interesting things is that as soon as we put differential stress in the system, we completely kill the tremor-like signal, and we don't see them anymore. So these are signals that we can only record under hydrostatic conditions, and this is probably the reason why we had never recorded them before. Okay, so the first conclusion of my talk is that the serpentine, on this part at least, the serpentine dehydration is accompanied by low P wave velocity. The reaction products, although denser, are softer because of fluid-filled crack inclusions. The elastic properties of fluid plus solid aggregates, in fact, are actually complex at subduction zone PD condition, and you need careful effective medium extrapolation to actually interpret them. And ours, at least, suggests that serpentine dehydration may provide a reasonable explanation for the high VPVS ratio regions. And in the absence of differential stress, we observe tremor-like A waveform, again, so that's also compatible with the observation in subduction zone. They follow the Gutenberg-Richter statistics, and they are observed at the right dehydration subduction zone PD condition. And former experimental studies of tremors had actually mainly concentrated on volcanic tremors, and the work of Phil Benson, and then the work on Luigi Berlini, and there is also the work that we did a few years ago on gypsum, but with Nicolas Brantu, which were all actually observed at rather low pressure. And here we really extended the pressure range like by an order of magnitude. And one of the important things is that even under hydrostatic condition, the reaction is accompanied by the nucleation, the propagation of narrow fracture. This is how dehydration takes place in the field. Even at high pressure and temperature condition, and so which in the presence of a differential stress may lead to dehydration-driven stress transfer, as proposed by Thomas Ferrand and co-authors a few years ago, basically where if you have an olivine here, some mantle partially hydrated, as you dehydrate those places where you have serpentine, basically you will transfer the stress to large regions that are actually stronger and not hydrated, which might eventually fail. And so you don't need a lot of hydrated material in the mantle to actually trigger these intermediate depth seismicity. Okay, so if I have, how am I doing on time? I don't know.
You have lots of time.
Okay, very good. So then we can. So now I will show you some recent experiments that we've done on this time in even how phase transition can trigger earthquake in the absence of fluids. So in this case, we concentrate on the olivine spinel. Spinel is understood as the high pressure form of olivine, Watzleyite and ringwoodite. So I always like to say that we all know that olivine is green, but ringwoodite is blue. So potentially 400 kilometers below our feet, there is a 200-kilometer layer of blue. And actually, it plays its importance because you can put some water in ringwoodite, and it's potentially, this is a complete side note, but the largest water reservoir on Earth might actually be in this layer of ringwoodite, 400 kilometers beneath our feet. So olivine transformed into ringwoodite through an intermediate phase Watzleyite. We go from orthorhombic to cubic, so it's a polymorphic phase transition this time. And so a few years ago, working on the in the lab, it's actually very hard, although Japanese colleagues just did it, to study the true olivine ringwoodite or olivine Watzleyite ringwoodite transitions, because it happens at very high pressure, the first around between 14 and 20 GPa. And so one way to circumvent that problem is to work on the germanate analog. Here we use germanium. The germanium replaces the silicon atom in the structure of olivine, and hence the transition happens almost an order of magnitude below in terms of pressure. And a few years ago, we showed that we can actually produce acoustic emission during the transformation of olivine spinel at 4 and 5 GPa. After that, and some colleagues in Chicago used hypo-DD location methods. And here you see a tomographic image of a sample that is faulted. And here you see the location of two subsets of acoustic emission. Obviously, it's its relative location because it's hypo-DD, but you can actually see that they seem to follow rather well the fault that actually are observed in tomographic image. And so there is a reasonable, it's reasonable to think that actually this fault did produce these AEs, and these AEs do follow Gutenberg-Richter law. So like we're talking now about millimetric sample that actually fell at 4 or 5 GPa along faults, and those faults produce Gutenberg-Richter scaling, etc. And if the puzzling thing back then was that if you look at this fault, they are extremely narrow. This is now 250 nanometer. This is one of this fault. And this fault is actually, this is olivine, and this is ringwoodite. So this fault is cooled with high pressure nanocrystalline ringwoodite. And so one of the problems with synchrotron experiments is that it's very hard to be systematic because you don't have a lot of synchrotron time, and to perform long experiments in the synchrotron is kind of an oxymoron. So one of the things is that in the Griggs apparatus we can produce long experiments, and Julien Gasque has done a full new set of experiment on the germanium olivine. Here I show you something like a half a dozen experiments performed as with increasing temperature. So the red one are the very hot one. This is the very cold ones. You see that when it's cold, it's actually this is the stress strain curve, goes to very high 2.5 GPa and then breaks. And this here you have at lower spread at higher temperature you have some sort of a subtle softening, but kind of a ductile behavior. And one of the nice things is that we can record acoustic emission in all these experiments. And what you will see is that some experiments here produce a lot of acoustic emission, and they are either the very hot one here or the very slow one, because we also did some experiments at 10 to the -6 strain rate. Whether the really cold ones here produced not so many acoustic emission, but very large ones, basically. So this is the energy, the cumulative energy released by acoustic emission. And so we have two sets. We have experiments that produce a lot of acoustic emission, but these acoustic emission have little energy. And we have here a set of experiments that produce little acoustic emission, but then these acoustic emission have a very high energy. And so, I mean, obviously that actually points to a temperature dependence of the B-value. So this is experiments performed at 700 degrees C, where you see that we have a B-value around 0.5. And here, this is experiments performed at 850 degrees, where we have a B-value of around 1.5. And so there is a temperature dependence of B-value observed in these experiments. We also think now we understand a little better the way the faulting and the the mechanical instability grows. When we look at our samples, in blue here is underlined the reacted part here, and you see that the reacted part always looked like this, like a finger that actually narrows down, and so and actually narrows down as it deviates and turns to 45 degrees or 30 degrees. And so this, in fact, we can understand pretty well if you couple the concept of stress inclusion with kinetics. Basically, if you imagine that you have even a spherical inclusion, or a little bit elliptical in that case, inclusion that actually starts to transform, because of the application of stress, there will be here stress concentration at the tip. And if you have stress concentration, the stress concentration will act positively on the reaction kinetics through the here this term, which is the pressure term in the Arrhenius equation. And basically the kinetics will be a bit faster here than it will be on the side, because here on the contrary, you have a depletion of stress, and so the kinetics will be a bit smaller, and hence the system will grow more and more elliptical, and at one point it will actually fail, because in the end you're producing very small soft product at the tip of these inclusions here. Okay, so to test this hypothesis, one thing you can do is you can plot strain rate in the compiling all the experiments yet done in this system as a function of growth rate. So the growth rate of the high pressure phase. So it's a proxy for the kinetics. And what you see is that there is a regime here where the sample is strong and ductile. There is no faulting. There is a regime here where the reaction here is actually very fast. And so basically we'll release all the stress that is imposed by strain rate. And then there is a window here, which would be called the transformational faulting window, which is the window where we observe acoustic emission and faulting. And you see that this window kind of follows in this plot, it follows a line here. And this line, if you gave it an activation energy, would be 250 kilojoule per mole. And that actually is more or less the activation energy of the reaction, of the kinetics of the reaction itself. So basically, what you're looking at is that if you are very fast, then you need to be very cold. But as you go slower and slower in this system, basically you will have instabilities at higher and higher temperatures, because what is important is the competition between the natural strain rate and the transformation rate in this system. This is actually quite nice because you can maybe try to extrapolate this window. So this is what Julien did. So this is the transformational faulting window extrapolated now to strain rates that are the strain rates of subduction zones, or a bit faster actually. So you see the transformational faulting window, and in fact it does intersect more or less the condition that we expect for slow and fast subductions in the world. So basically, where if you assume that in these subductions you could have strain rate of 10 to the minus 9 to 10 to the minus 11, as actually shown lately by a paper of Magali Bilen, indeed, there is the possibility for this transformational faulting window observed here in the lab to be extrapolated in this condition. This has so now comes the problem of how in our system here, when it's hot, we produce a high B value, sorry, and when it's cold, we produce a low B value. And this is kind of, sorry, I have to go back all the way to the beginning, sorry, for the people who are a bit, okay, so this is the contrary to what is observed here by Zhongwenzan, where basically hot subduction zones have a low B value and cold subduction zones have a high B value. So this is the exact opposite. So in order, we have to find a way to reconcile that. And so, sorry again for the slideshow. And so one of the ways to reconcile that is to say that, in fact, in cold subduction zones, what you're looking at is the failing of the entire metastable olivine wedge. So here you have a reconstruction for Bolivia, where basically this is in shaded gray here would be the metastable olivine wedge at depth. Here this would be this box here, and you produce earthquakes in the metastable olivine wedge, and some of them have to actually propagate outside of it. And this is the question is, how can they propagate outside of the metastable olivine wedge? Whether in very cold slab, in fact, you never break the metastable olivine wedge, but you have actually the double layer of like transforming material with small earthquake, which is hotter, and you actually have this double layer, which has been observed by Doug Vince in a paper in 1993. So the idea is that if you have a high thermal parameter, cold subduction zone will have a large B value because the earthquake are confined into both sides of the mole, which is undergoing transformation. Whether we're in a low thermal parameter, you have a low B value because earthquake may initiate inside the mole and by some magic way must propagate outwards. And so hence we did the sandwich experiment. So the sandwich experiment is sorry, I make myself laugh, probably nobody else is laughing, but the sandwich experiment is an experiment where it's an olivine spinel sandwich, where we have a slab of olivine here that is actually in between two breads of spinel. And we looked whether faults that actually propagate inside the olivine could actually propagate outside of it. And you see that a number of them stop, but some of them actually can propagate all the way through. And if you look at what is inside the material where it propagated all the way through, you have those crazy textures here that are actually indicative of melting. So inside here, you have transformational faulting where like really linked to the reaction. And because the tip may carry enough energy that actually can actually break into the rather stable olivine spinel part via frictional melting. Okay, so this is the conclusion of the second part of the talk. So transformational faulting seems to be controlled by the competition between natural strain rate and transformational strain rate. And that actually is a very nice thing because it enabled us to possibly upscale at natural slab conditions. So high temperature, slow strain rate, we see a high B value, low temperature, fast strain rate, we see, sorry, a high B value, low temperature, fast strain rate, we see a low B value. We somehow try reconcile that with the sandwich experiment, maybe. Okay, so the mechanism of triggering itself seems to be linked to the fact that where there is stress concentration, you can have faster kinetics and then basically even a spherical inclusion will end up being growing in aspect ratio, etc. And probably also the fact that the reaction is exothermic itself and that there is reaction softening due to nanometric grain size of the reaction products plays a role. And finally, transformational faults can propagate outside the mole, the metastable olivine wedge via frictional melting. And so maybe more general conclusion. So I think we've seen in many talks over the last years that I think the time source seismology could really neglect the host medium contribution is some sort of a bygone era. So we need to now incorporate the medium itself and its contribution in terms of energy and work to the system during all the phases of the seismic cycle. And via phase transformation, in fact, the medium can contribute work, whether the reaction is, produces positive or negative delta V, and heat, whether it's exothermic or endothermic. And so that actually can be done either the interseismic or co-seismically. And so I think clearly phase transformation, because we're talking about a large amount of energy, again, stored and released in minerals, it should probably be taken more into account. The nice thing is that there is a concept in thermodynamics, which is the Clapeyron slope, which is delta S over delta V, so which actually precisely measures the work contribution relative to the heat contribution of every phase transformation. And it does, and thus this Clapeyron slope provides immediate information on the mechanical stability of a phase transformation. And for instance, the one transformation that actually has negative delta V and also is endothermic is the olivine gamma gives bridgemanite plus magnetoversatile, which is the lower limit of seismicity ever observed on Earth. Okay, so we should also consider thermodynamics properties of water. And I want to say, and this is just for my own thing, that the thermodynamics of solids under stress remains a field with almost no laboratory data. So it would actually be nice that people start to produce them. Okay, thank you very much for your invitation and your attention.
I'll invite everybody to unmute turn on their camera if you'd like to and join us. And thank you, Alex. Really great talk, Alex. Thank you. Yeah, okay, lots of interesting stuff. So easiest thing for us to do is to use the reaction button on the bottom of your screen and raise your hand to put us in order of asking questions. And this won't be the last time, but I will do it. It won't be the last time that I say, especially for early career people, participate, raise your hand, ask a question, and we can blast away. We'll give Alex long enough here to catch his breath, and then he can answer a question by John Rudnicki.
Alex, thanks for a wonderful seminar. I've known you since you were a student, and this is the first seminar I've heard from you. So I've been missing a lot, I realize. So my question's a naive one and probably simple, but in the first part of your talk, you get these narrow zones forming under hydrostatic stress, but they go away with non-hydrostatic stress. And I would have thought it was the opposite. And when they form under hydrostatic stress, is that because locally the sample is very inhomogeneous because of these reaction fronts, or yeah,
so thank you very much, John, for your comments and for everything. In fact, all these experiments were produced under hydrostatic stress. Obviously, you see that the reaction always starts at bottom. So we do have a thermal gradient problem in our machine. And it seems that when the kinetics of the reaction is actually slow, so at low pressure here, at low temperature or high pressure, so this is when you are actually the closest to equilibrium, it seems that the reaction mainly happens via fracturing, probably because this is how you can expel the fluid out. As you increase the temperature, or at low pressure here, basically, the kinetic of the reaction is actually faster. In fact, if you look at the, how do you say, the écart, how far you are from equilibrium, you see that this experiment is the furthest away from equilibrium here. And so basically you switch to a system where the reaction happens making a reaction front. So again, this is showing that in our experiments, first, there is normally no differential stress, but there is because there is a temperature gradient. Yeah. And when the reaction is slow, this competition between the reaction rate and the strain rate linked to the temperature, basically the thermal strain rate, basically will do fracturing, whether when the reaction is fast, we have a reaction front, and this we don't really understand at this point, I must say. I mean, I should have said that from the beginning. We don't understand, sorry.
Okay, no, thanks for the clarification. Again, great seminar.
Alex, fabulous talk, really, really interesting, lots of interesting stuff. And it's, yeah, it's nice to be taken down deep into the earth to think about things that are happening under these incredible conditions, really complicated. Two quick questions. One on this plot right here. Let's see, so we're under hydrostatic conditions, but on the top right, especially, we see something that looks like it was subjected to shear. You know, we see in the sensory phosphoride case, we see something that looks like it's got shear offset even. How does that happen?
Well, so this is a good, also a very good question. I think this is clearly the limitation of the Griggs apparatus. Probably David Goldsby can comment better than me on this. I mean, this is a solid medium apparatus, and I mean we're never completely hydrostatic. What I can tell you is that these faults and this shear offset were produced under differential stresses that are not resolvable
Okay.
with the Higgs apparatus. So
I see.
probably below 100 MPa or 100 MPa or below.
Okay, yeah, I see, I see. Or, yeah, or maybe there's just some way that the reaction kind of starts in one section and generates its own shear stress.
Yeah, exactly. So clearly, also because we have a temperature gradient in the system, there will be differential stresses created by the temperature gradient in the system. So, and this, the magnitude of them, we didn't compute at all, but it's a good question.
Yeah,
We could potentially compute them.
Yeah, I see. Okay, thank you. And okay, seeing no other hands raised. I want to ask one other quick question, and it involves something you had in your conclusions about the relationship between transformation and dilation and the possibility for dilatancy hardening. And maybe, yeah, mind hearing just a little bit more about how you would manage to get dilatancy hardening. Maybe I just need to think about
Yeah,
it.
so actually, so maybe maybe the reaction of serpentine will be a good way to explain that. So you see all the dehydration that are phase diagrams always have this bell shape here that you see.
Yes.
With some sort of a, the first thing is that they're almost always vertical because they actually are mainly thermometers. They are controlled by temperature, and then they have this bell shape. However, because this is always delta S over delta V, so this, the variation, the enthalpy, reaction enthalpy divided by the volume of reaction at low pressure. Here, the products the products of the reaction actually have a larger volume than the reactant themselves. So which is why the Clapeyron slope is positive, and then it turns negative at high pressure because water is a highly compressible medium, and in fact at high pressure water becomes extremely dense, and so even though you're dehydrating your material, you're creating more porosity than actually the water was taking more place inside the mineral assemblage than it is taking outside of it.
I see. Yeah.
Okay? And so basically, this would be a good case of dilate and hardening. Okay, like the transformation is generating a negative delta V, and so this is kind of the pore pressure should go down in these conditions. However, because I mean,
yeah, see, yeah, okay, yeah, super cool. And so, wait, and do you? So that predicts a kind of a transition in your VP.
No, so this is a good. So as you could see, we could not go higher than 2.5. We tried to go to 3 GPa, but we broke several base plates, so we couldn't go really in the negative delta V domain. We could go. I mean, we could go in the delta V equals 0. And in fact, what you see here is at high pressure, you see that the P wave velocity drop is much smaller than at low pressure. And this is not due to the amount of reaction. The reaction extent was almost the same in these experiments, but this is just due to the fact that water becomes so dense at 2.5 GPa that basically it doesn't slow down the waves anymore. I mean, not as much.
I see. Cool, thank you. Georg.
Yeah, Alex, great talk.
Georg.
And hi. And you know, a lot of work. So a question that I had that occurred to me when you showed your first slides was so you have your acoustic emissions, and it's not so many acoustic emissions, and you have the crack density that produce, I mean, the cracks produce the acoustic emissions and the reduction in the P wave velocity. So did you try to estimate how much energy is dissipated in the acoustic emissions compared to the total energy dissipation? we've done this for, I mean, you have done it, I
this-
think, we have
this
done it
is,
for,
this is a very good question. No, the fast answer is no, and the second answer is that we cannot do that for the moment because we have to decide at the beginning of the experiment for the moment whether we go for P-wave velocities or whether we go for acoustic emission. We don't have
Okay.
yet in the machine, we're not able to do both at the same time.
okay.
But I would expect that it's small. Again, as you said, that there is not many acoustic emission. Although those tremor-like signal, we've recorded hundreds of them in some experiments. So really, it's not, I mean, enough to have produced a Gutenberg Richter law. So
Okay, thank you.
Alex, you've made believers out of all of them, I guess, but
yeah.
so.
Turn everyone into mineralogy matters.
Yeah, hi, Alex, this is Bill. Let me ask you a question if I might. So recently, Xanthopy Markinskoff has been talking about an idea of purely transformational strain as a mechanism for deep focus earthquakes, in which an inclusion would grow as a pancake with shear.
Yes, okay.
Do you think you can test between that and the presence of, you have shear faulting in your models, I understand, and once you nucleate, you've talked about having propagation outside of the zone. Do you think it's possible that you could look more at the transformational model using this particular apparatus?
Yes, so we discussed a lot with Xanthopy a few years ago. I think, well, first, I think this is a way, the model of the dynamic Eshelby solution is way above my mathematical understanding of things.
Mine too.
And but it's really a very beautiful. I am quoting Harshabat here. It's a very who probably gets part of it. So it's really a very beautiful development. I think that I don't know whether we can test it. We had long discussion. One of the things that we see systematically is that the kinetics plays a huge role, and so I think that the work that we started a few years ago with Nicola, and that actually that Jim Rice and one of his students, now I forgot his name, did. Where we can incorporate mineral transition and kinetics. I mean, in a more simple, like like thermal pressurization problem, like for me at least is easier to grasp. But how to implement that into the dynamic Eshelby solution, I don't know.